Alright, so today we're going to be covering a trick to do integration using partial fractions. So partial fraction decomposition to solve integrals. And so, for example, let's say I think like the best way to do this is just through a lot of examples. So let's just start with that. So the first example is we want to integrate 5x minus 3 divided by x squared minus 2x minus 3 dx. And so this sort of the integrand, right now we don't really have any tools that we can use to find a antiderivative for the integrand. And one thing that we do know is if we have something in the form of 1 divided by some term that has an x term to it, we know that the antiderivative of that is simply ln x. And what partial fraction decomposition allows us to do is it allows us to decompose a fraction into terms that can get us in this sort of form that we actually know how to find the antiderivative of. And that's the whole notion behind using partial fraction decomposition to solve integrals. So given that, whenever we see that the denominator is factorizable, so here's the denominator, we can factorize it into x minus 3 times x plus 1. And we don't readily know, can use any techniques to integrate this whole fraction. We can use partial fraction decomposition to decompose this fraction into two fractions, and then we can integrate both of those, the sum of those two fractions. And then, yeah, I'm going to assume that we're all familiar with partial fraction decomposition since this is not the focus of the video, but if you want me to make a video covering partial fraction decomposition, just let me know. But we basically want to decompose our original function into these two fractions where a and b are the numerators. Right? And so the system of equations that we get over here is ax plus a plus bx minus 3b is equal to 5x minus 3. And so taking the like terms over here, we get a plus b is equal to 5, whereas a minus 3b is equal to minus 3. Subtracting, we get 4b is equal to 7, and therefore, we have 5x minus 3, ax plus a, and then bx minus 3b, and then a plus b is equal to 5, a minus 3b is equal to, this is 4b is equal to 8, and so b is equal to 2, and then a is equal to just 5 minus 2, which is 3. And therefore, our original fraction can be represented as the same as the integral of 3 divided by x minus 3 plus 2 divided by x plus 1 dx. And notice how now, once we have decomposed the original fraction into two terms, we already know the antiderivative of each of these terms because we have the form of 1 over x. And so the antiderivative will simply be 3 times ln of absolute value of x minus 3 plus 2 times ln of absolute value of x plus 1 plus c. So partial fraction decomposition allowed us to find the antiderivative of our integral. And that's the whole method. And that's the general gist of using partial fraction decomposition to solve integration problems. And let's just look at more examples so we get better at spotting when we can use partial fraction decomposition. And so the next problem is we want to find the integral of 6x plus 7 divided by x plus 2 whole square dx. And the reason I included this is because this includes another case of decomposition that we might have forgotten. So we can decompose this into a over x plus 2 plus b divided by x plus 2 squared. And that we want equal to 6x plus 7 divided by x plus 2 squared. Therefore, we have a times x plus 2a is equal to, because I'm multiplying a by x plus 2, right? So a times x plus 2 is ax plus 2a plus b is equal to 6x plus 7. A is the only one with an x term, so we can easily find out that a is equal to 6. And 2a plus b is equal to 7. And so if we plug in a is equal to 6, we get b is equal to -5. And therefore, our original integrand can be re-expressed as the integral of 6 over x plus 2 minus 5 over x plus 2 squared times dx. And notice how both of these terms we can find the antiderivative pretty simply. So for the left term, this is simply 6 times the ln of absolute value of x plus 2. And then on the right side, we get -5 times x plus 2 to the -1 divided by -1. So then we just flip the sign, so it'll become +5 times x plus 2 to the -1. And we can re-express this whole thing as 6 ln of absolute value of x plus 2 plus 5 divided by x plus 2 plus c. Again, I hope you guys notice how decomposing this original fraction into its partial fractions is the only way for us to easily find out the antiderivatives. Let's look at a third example. So example 3. We want to find the integral of 2x cubed minus 4x squared minus x minus 3 divided by x squared minus 2x minus 3 dx. Again, it looks like this integrand cannot be readily we cannot find the antiderivative off the top of our head for this. So since the denominator is factorizable into x minus 3 times x plus 1, we probably will be relying on partial fractions. But before we can decompose our numerator, notice how the degree of the numerator is greater than the highest degree in the denominator. So before we have partial fractions, we must actually find the quotient, and that will be taken out separately. So we have 2x cubed minus 4x squared minus x minus 3. And then we are dividing that by x squared minus 2x minus 3. So recall long division, and that's exactly what we're doing. So the first term is 2x, so I have 2x cubed minus 4x squared minus 6x, and then I subtract. These all cancel out. I'm left with 5x minus 3, and that will be my remainder. And so this original fraction, it's re-expressed as the integral of 2x plus 5x minus 3 divided by x squared minus 2x minus 3 dx. So we already know how to integrate 2x. We just have to deal with integrating that, the second term, and we can use partial fractions to do that. So let's work with that. So we have a divided by x minus 3 because of these factors, plus b divided by x plus 1 is equal to 5x minus 3 divided by x squared minus 2x minus 3. So I get ax plus a plus bx minus 3b is equal to 5x minus 3. Now these are the two terms with the x, so a plus b is equal to 5, and then a minus 3b is equal to -3. Subtracting, I get 4b is equal to 8, and therefore b is equal to 2, and a is therefore equal to 3. And so finally, our integral looks like the integral of 2x plus 3 divided by x minus 3 plus 2 divided by x plus 1 dx. And therefore we can finally find the integral of this by finding the antiderivative of each term, and this is simply x squared plus 3 times ln of x minus 3 plus 2 times ln of x plus 1 plus c. There it is. Let's continue doing more examples. This one is an initial value problem. Initial value problem. So we want to find the solution to dy over dx is equal to 2xy times y squared plus 1 that satisfies y of 0 is equal to 1. So we can clearly see how this differential equation is separable. So we know how to solve separable differential equations. We take dy divided by y times y squared plus 1. That is equal to 2x dx. And now I'm going to take the integral on both sides. The integral on the right side is pretty easy. This is just x squared plus c. The integral on the left side is a bit more tricky. And it seems like we'll be using partial fractions again to solve for this. And so the decomposition of 1 divided by y times y squared plus 1 is simply equal to a divided by y plus by plus some value c divided by y squared plus 1. And this decomposition again follows from the rules of how to find the partial fraction decomposition. And if it's confusing and you want me to make a video on it, just let me know and I can cover partial fractions more in depth. But through this equality, we get a times y squared plus a plus b times y squared plus cy is equal to 1. Therefore, a plus b is simply equal to 0. C is also equal to 0. And a is equal to 1. And because a is equal to 1, b is equal to -1 because of this equality. And now we have decomposed our left integral into simply the integral of 1 over y minus minus y divided by y squared plus 1 and then times dy. So this over here is simply ln of absolute value of y, and then to solve for the integral of minus y over y squared plus 1 dy, we need to use a substitution. So if we substitute the value w is equal to y squared plus 1, we get dw is equal to 2y times dy, and therefore dw over 2 is equal to y dy. And so we can re-express this as the integral of dw divided by w times 2. And so that is the same thing as 1/2 ln w, and I'm going to resubstitute the value for w as y squared plus 1. And I mean, we can remove the absolute value since y squared plus 1 is always positive. And now in totality what we have is we've gotten this, and we have gotten this. So let me just rewrite everything in the space over here. I have ln of absolute value of y minus 1/2 ln of y squared plus 1 is equal to x squared plus c. Now we need to solve for c, and we can solve for c by using this initial value that we have. So y of 0 is equal to 1. So ln of 1 is simply 0. Here we get minus 1/2 ln of 1 plus 1, so ln of 2 is equal to c. So therefore if we take this if we take the square root inside, we get minus ln of root 2 is equal to c. And so finally, our solution to the initial value problem, and we're not going to explicitly solve for y, we're going to keep it an implicit solution. We have the natural log of the absolute value of y minus 1/2 ln y squared plus 1 is equal to x squared minus ln of root 2. And so hopefully you guys followed along and realized that the only way we could have arrived and solved this initial value problem was through the use of partial fraction decomposition.